Hi, you have stumbled upon Allen High School's APIB chemistry class, and we're discussing thermochemistry and thermodynamics. Let's take a look at this next question. It says, answer the following. Be very careful. Read carefully. You can't have a highlighter or a pen, but you can have a pencil. And by the way, this is a non-calculator. This would be a Part B question. Notice that it says answer in terms of thermodynamics and kinetic molecular theory, which is rather interesting because we're talking about thermo, not kinetics and collision. So that'll be interesting to process as we get going. But those are the two key points we want to focus on. Now, the first question says indicate, and that's going to be worth a point, and justify. So in other words, we want to make a claim and then we want to provide evidence to support our claim. Now in this case, delta S, the entropy, is negative. So that's my claim. Now I have to justify or support that claim. And you may need a few more words than I'm writing, but honestly not too many. It's negative because it is less disordered. There's a loss of freedom. So less disordered or less free. I would hope they would accept that argument. It's not the most common one, but it helps me the most. Less disordered or less freedom because we went from 3 moles of gas, which is highly disordered, to a mole of solid and a mole of liquid, both of which are much less disordered. I like to just keep it in terms of disordered. A student once taught me that. She said it helps to keep that from being too confusing because a positive is an increase in disorder. So it's less disordered. So then what happens is we end up with an overall negative here. All right. So it tells us, the question indicated that we have a spontaneous reaction. That would have been another thing I would have noted right away. And it also gave us this enthalpy value. All right. Now, spontaneous, since it's spontaneous, that means that delta G naught is negative. All right. Delta H naught is also negative or exothermic, which is favorable. Okay. Delta S naught is negative, which is unfavorable. So unfavorable things don't drive spontaneity. Favorable drives spontaneity. So this would be considered enthalpy driven, because when it is spontaneous, that spontaneity is driven by a favorable enthalpy. So that's my driving force for this reaction. Okay. Now, in the next one, it says if we increase temperature, what's going to happen to delta G? Well, remember, an increase, I hope you remember. If not, I'm going to refresh your memory. An increase in temperature is going to increase the entropy component. Remember, delta G is equal to delta H naught minus T delta S naught. So if you increase temperature, you increase whatever contributing factor is played by the entropy. So if I increase the temperature, I increase the entropy. Since that is, in turn, an unfavorable process, okay, an increase in entropy would lead to a less spontaneous reaction. Okay. Now you can argue that from the formula as well. This is negative. This is negative. A negative times a negative is a positive. So as I increase temperature, my delta G naught becomes more positive, which means less spontaneous. So that would be another approach there. Now, this is where the kinetics come into play. Do you notice that it says that Delta G is known to be spontaneous, but it doesn't proceed at a measurable rate at room temperature. Account for this, now notice the key word here, apparent contradiction. And here's the key. Spontaneous, the word spontaneous is about the energetics of the process. It's about my balance between my enthalpy and my entropy, and it's a question of final minus initial, a state function. Rate, the key factors in rate, in addition to concentration, are activation energy. Okay, so if I could really exaggerate this for a minute, all right, here we go. There would be, do you remember these diagrams? Let me even exaggerate that a little bit more, okay? So I could have a situation where it is spontaneous with a huge activation energy. All right, so it may be spontaneous because of my balance of enthalpy and entropy, but the activation energy means it's going to go slowly. And so that's why there is not a tight link between the energetics and the kinetics in this sense. Spontaneous doesn't mean fast. Radioactive decay occurs spontaneously, but there are some reactions that require tens of thousands of years to proceed. All right, now the next one is similar in terms of kinetic molecular theory and our knowledge of reactions. It says a catalyst increases the rate. What does it do to delta G? Well, there's a couple of ways that you can look at this. For one, you can evaluate in terms of delta H. Remember, products minus reactants on a potential energy curve gives us delta H. Okay? A catalyst decreases the activation energy. It's a good thing I'm not an artist. Okay, sorry, that's really bad. But anyway, it decreases the activation energy, but it does nothing to my enthalpy. So enthalpy is constant. Okay, entropy has to do with their disorder in their final states compared to the initial. So delta S is constant or remains unchanged, and therefore delta G remains unchanged. All right, so the key thing here is mentioning that a catalyst decreases the activation energy. Some other terms you could use here is this does this by providing an alternative pathway with a lower, let's say a new activated complex or stabilized. So new or stabilized activated complex. But here's the deal. What kind of function is delta G? Well, delta H, delta S, delta G are all state functions. So this new pathway has no effect. Now, it's going to get there faster. It's certainly going to impact your reaction, but it has no effect on these values because they're independent on pathway. They only depend on final and initial. So this was key. The question required you to discuss what a catalyst does and then why, either from here or here, why it has no impact on the reaction rate. So that's one of our questions. I'll do two more for you to help you study for your test. So until the next one, this is signing off.